Section 5.6. This is a very important section in determining and using the coefficients that you've worked so hard to balance, and to use them to do the math in as we do more and more sections. These numbers are more than just a balancing of the atoms. These numbers also are going to give us this particular relationship that we can convert from mass of one item to moles of it, to moles of another item, to then mass, which we'll understand later. So just follow us through here and understand these. It's a very important concept here. Now you'll notice that here's our real representation of 2 moles of silver right here, 215.8 grams. And the coefficient in front of the S, there is none, so it's understood to be 1 then. So for 1 mole of sulfur, you look up the molar mass of sulfur, it's 32.1 grams. So when it makes the product of our silver sulfide, you'll notice the coefficient in front of that is, there is none, so that means 1 mole, and 1 mole of silver sulfide is 247.9 grams. We know how to figure out the molar mass. We practiced it a few sections back, so you can calculate that, and that is that. But something else interesting is, if you were to actually add up the 215.8 plus the 32.1, it does equal 247.9. Well, let's see why. Because the law of conservation of mass indicates that in an ordinary chemical reaction, matter cannot be created or destroyed. There is no change in total mass that occurs. The mass of the products is equal to the mass of the reactants. So when we look at this particular table here, we can get a lot of information from just our balanced equation. Our 2Ag plus S gives us Ag2S. So you'll notice that we can do it from atoms. We can convert it. That means Avogadro's number because it's the amount of atoms. The biggest thing is it's a ratio, 2 to 1. So we could have 2 atoms to 1 sulfur atom. We could bump it up, convert it to, and multiply everything through by 100. So that would be 200 to 100. The point is it's a ratio, 2 to 1 ratio. We could apply this to Avogadro's number of atoms. And since moles is a number of atoms, this also applies to, and here's the key, that this number here applies to 2 moles of silver and to 1 mole of sulfur. So it is a 2 to 1 ratio. And over here, the coefficient in front of this, which there is none, is understood to be 1, so it is also a 1 mole of our silver sulfide. So here's another equation. Consider the following equation. 2Fe plus 3S yields iron 3 sulfide. This equation can be read in moles by placing the word moles of between each coefficient and formula. So really, if we were really reading it, 2 moles of iron plus 3 moles of sulfur is going to give us 1 mole of iron 3 sulfide. So here's our key here. A mole-to-mole factor is a ratio of the moles for any 2 substances in the equation. So we can compare iron to sulfur, we can compare iron to iron 3 sulfide, and we can compare sulfur to iron 3 sulfide. And in the comparison, we're going to set up our mole-to-mole ratio. So we just got to figure out in later equations which one goes on top. Well, it depends on what they're asking for. So let's first realize that the relationship between our iron and our sulfur is that we have 2 moles of iron for every 3 moles of sulfur. We could have also written it as 3 moles of sulfur for every 2 moles of iron. The relationship for iron and iron 3 sulfide, for every 2 moles of iron, it is 1 mole of iron 3 sulfide. Or we could have reversed it and said 1 mole of iron 3 sulfide is 2 moles of iron. Notice we didn't just reverse the numbers, we reversed the entire unit factor. So 1 mole of iron 3 sulfide. Between sulfur and iron 3 sulfide, notice there's a 3 in front, so the mole-to-mole factor or mole-to-mole ratio is 3 to 1, or we could have said 1 to 3 on our moles. So let's pick out on this following equation, consider the following equation. Which of these ratios for hydrogen and nitrogen is correct, is what they're first asking. Well, We have 3 moles of hydrogen to 1 mole of nitrogen. Let's see what that ratio is. No. 1 mole of nitrogen to 3 moles of hydrogen. Yes, we could have written it either way. That works. So that is number 2. So B. Let's compare the mole-to-mole factor for ammonia and hydrogen. So NH3 and H2. So we're going to have a 2 in front of the NH3, and there is a 3 in front of the H2. So let's see which one of those is that. No. And so we need 2 moles in front of the NH3, yes, and 3 moles. Yep, that's exactly right. So we have a 3 here, so this one fits the correct ratio. And that explains it here. So now then, let's apply this in an additional step. So let's do some calculations now. How many moles of iron 3 oxide can form from 6 moles of oxygen? Well, we know that we can use this relationship that we've worked so hard to balance to convert from moles of one item to moles of the other. So we're going to use the 3 moles of O2 to 2 moles of Fe2O3 because those are the labels that they ask for. And we'll do that by using our mole-to-mole factor to determine the moles of our iron 3 oxide. So we start with what's given, 6.0 moles of O2, 6.0 moles of O2. Now then, you know, we had this ratio of 3 moles of O2 to 2 moles of Fe2O3. The question is which way are we going to use it and set it here? Well, our moles of O2 must cancel out. That's what was given. So that means the 3 moles of O2 must be on the bottom of our ratio here. So we're going to have 2 moles of Fe2O3 to 3 moles of O2. The moles of O2 cancel out, and you get 6 times 2 divided by 3, which is our 4.0 moles of our iron 3 oxide. So let's do some more practicing and our guide. Obviously, we need to state what's given and what's needed. Figure out our plan. Use our coefficients to write the relationships, mole-to-mole factors. Set up the problem using the mole-to-mole factor that cancels out the labels of the moles. So how many moles of Fe are needed for the reaction of 12 moles of O2? So here's our equation. They give us some different choices. So the first thing we need to do is we need to look back to see what's given. Well, 12 moles of O2 is given, and they want to know how many moles of Fe. So we need to then look and see what is the relationship of our equation. Well, let's look and see. The coefficient in front of the O2 is 3. The coefficient in front of the iron is 4. So we know that we can either have 4 moles of iron over 3 moles of O2, or we can invert that ratio, that mole-to-mole, to 3 moles of O2 to 4 moles of iron. There's only one correct answer in this question, so we need to figure out which way we need to do it. Okay? Well, we're going to set it up. We first start with what is given, the 12 moles of O2. Right then and there, that tells us which of our ratios we need to set up. We need to have our moles of O2 cancel out. So that means the moles of O2 must be on the bottom. So our ratio is 4 moles of iron over 3 moles of O2. So 12.0 times 4 divided by 3 is 16.0 moles of Fe. Let's do one more. Using the following equation, how many moles of ammonia could we obtain from 4.8 moles of H2? Press pause, see if you can do this. Now remember that the coefficients in the balanced equation represent mole-to-mole ratios, so we set up the conversion to cancel out the moles of H2. Why? Because that's what's given. So let's see here. 4.8 moles of H2 is what we start with. We're going to need to set up our conversion of our, using the 2 coefficient, 2 moles of NH3 over the 3 moles of H2. We need to set it up this way so that the moles of H2 cancel out. So our moles of H2 cancel out, so we're going to have 4.8 times 2 divided by 3. And your answer is going to be 3.2 moles of NH3.